I have to say that it will be hard to match the speaker before me. But I'll try at least to show you something interesting. And before that, I would like to express my great appreciation to the organizers. It's really hard to put together a meeting, and I think they deserve from us a little round of applause as well. Yeah. With that, I also would like to say that it's quite exciting to be a part of the rapidly evolving academic field. It's stimulating to be among the people who would look at the same thing from a very different points of view. And I would like to offer you the my understanding of chirality at nanometer scale, and in particularly I would like to address the transition from the molecular scale chirality to the greater scales of chirality, in particularly to nanometer and submicron scale. And I want to say that for us, the journey started with a scientific question: how complex, in general, the assemblies of the nanoparticles can be. And we thought for quite some time that the nanoparticles that you can see here, they actually in size and in interactions, they have a lot of commonality with the proteins. And the question, in fact, was at some point, can we make the structures as complex? And here is the example of a terminal assembly of the proteins in the membrane. And I think at this point, I have to say that possibly from inorganic nanoparticles, considering all the polydispersity, we possibly can, but we should try at least. And the recent example, or actually a couple of years ago, example of such assemblies that you can see here, these are from isotropic particles of cadmium-T and the proteins. And the gold part, the solid part, are the particles of semiconductor. The transparent part are the proteins. And it's not a complex structure in terms of the geometry, but it's sure quite complex structure in terms of the functionality. And what we would like to do is actually to plug in the anisotropy and the chirality that we know exists in the proteins and achieve it into the assemblies. And from that time, we were quite attuned to the property of chirality in nanoparticles. And we started looking at the circular dichroism in a number of assembled structures. And the first assembled structure that we saw, it exhibits very strong polarization rotation, was obtained by connecting gold nanoparticles by DNA in PCR process. And we postulated, or hypothesized to be honest, that this is due to the fact that DNA assembles differently sized particles in some kind of tetrahedron, asymmetric structures, if you want. And I have to say that eventually it was not a correct hypothesis, but in fact, in that structure, when we do the multiple cycles of PCR, asymmetric gold particles and asymmetric assemblies form. The fact that it is at the plasmonic part of the spectrum had led us to the need to look at some other potentially tetrahedral structure or asymmetric structures. And the question here we try to answer, if we have that strong circular dichroism, how do the particles know that they need to assemble in that tetrahedral, not at the other one? And so we decided to assemble them in a very controlled way. There are a lot of people who are interested in connecting nanoparticles by DNA. We thought that if we combine 4 different particles, one gold, which is big, one gold small, and silver, and semiconductor, we should have the tetrahedron. And indeed, we obtained that. That was the collaboration with my very good old friend and colleague, Professor Xu. We obtained a number of tetrahedrons, including the ones which have symmetry. The good thing here was that indeed we saw very strong polarization rotation. It is also at the plasmonic part of the spectrum. That was a very pleasant thing to observe. In addition to that, we also saw that we have peak here and very small, like a shoulder on the UV side. So we associated with the transition, with the plasmonic transition in silver particle and excitonic transition in cadmium mass. What we also included in that paper and highlighted our inability at that time to explain it was the fact that if we take just 2 of the particles and connect them with the DNA bridge, we also see quite strong polarization rotation. And if we look at the connection between one particle and the other, a part of DNA bridge over here, it is actually a symmetric structure. Yes, I mean, there could be asymmetries which are associated with a DNA, right? And I think Sasha will tell us how that can be translated in the plasmonic states. But what we saw, that there is too strong of a plasmonic adsorption, too strong of a plasmonic rotation in order to really be explained by this. And also, if we looked at the other types of the structures, for instance, these kind of pairs, as well as the ones from gold rods, they're also symmetric, or at least they are not, they don't have an obvious asymmetry, chiral symmetry. And we decided to investigate it. And that particular structure, that particular model initially led us to much better understanding of every single case of polarization rotation that you saw. And so what really it comes down to, that we don't have the parallel rods. And in every case, they actually have an angle here, and we looked at the transmission electron tomography that you can see here. And it is a statistical analysis of the images like that, that the angle there is about 10 degrees. Now, the question is, why do we still reference one angle against the other? That has to be present there in order to have the net polarization rotation. The answer here is not clear. I can offer you some thoughts about it, that it could be related to the mechanics that DNA strands connecting the two rods, they're twisting because of the twist of DNA. It overlaps with a lot of electrostatic repulsion here, and therefore it has the minimum state which is twisted, which is actually not very uncommon for holosteric liquid crystals. There is another twist in it, if you want, that gold rods, as we just have by using another type of electron microscopy, that they're actually excuse me, that they're actually anisotropic. So what we think about gold rods is not actually quite right. So this end is not the same as the other end. This plays in anisotropy of the twist. How? I don't quite know yet. I need to study it more. What is true that still that we can connect the polarization, rotation, and optical activity with the structures. And the researchers in Spain, Luis Morsan and Guerra, they have studied it also quite extensively in liquid crystalline structures. What we decided to look at the individual gold rod in collaboration with Stefan, and indeed we saw that from this one twisted pair we have the same CD signal with the same Kotov effect as in the bulk. And there are a number of other pieces of evidence, and one of those is the fact that we can actually change that angle. This is the case of ionic assembly when there is no DNA connection between one gold rod and the other gold rod. We just change the ionic strength around the rods, and they actually change the orientation, and that is reflected in the spectrum to the opposite angle. That was definitely quite exciting to see for us. So let's come back and talk about a little bit about why did we see such a strong polarization, rotation, and CD peak when we did PCR and thought that we have tetrahedrons with gold particles. Gold particles are not spherical. The models which are often used are actually not quite accurately describing the real gold particles. A lot of them, if not the majority of them, are actually oblong. The difference in one axis and the other axis can be quite small. It can be just a 10% difference and 1.1 ratio. And this is enough in order to get a twisted structure, just like with rods, in the connection between one particle and the other particle. All right, so now let's go to the other piece of work. That would be the chiral semiconductor particles. And there I would like to particularly address this molecular scale asymmetry and some other, besides the plasmonic optical properties, which are related to excitonic effects in the chiral nanoparticles. For quite a while, we thought that if the particles are tetrahedral and cadmium C, cadmium S, cadmium T particles have this very fundamental, very clear tetrahedral shape. If we cut them at the corners, they have to be chiral. Now the question is how to do it in a specific way. or how to have the particles which are L exceeding the particles which are R. We saw the evidence that the particles are indeed truncated tetrahedrons from the high-resolution transmission electron microscopies that you see here. It was done by Andrei Chuvilin in Spain with the help of Andrei Rogac. So what we eventually obtained and saw that these particles can, under conditions which are balancing electrostatic repulsion and van der Waals attraction, they can form these twisted ribbon-like structures. This was amazing for us. This was definitely a chirality in effect. Unfortunately, at that time, we were not able at all to see the enantiose selectivity in that process. So in that mixture of the nanoparticles, there are equal amount of nanoparticles, and as Thomas pointed out in the beginning, there is equal amount of particles which are left and right. And that resulted in the formation of equal amount of the wires. What we decided to do is to change that. We decided to illuminate that mixture with left and right circularly polarized light. And this resulted in the formation of left, if the light has the left rotation, and right, if the light has the right rotation, twisted nanoribbon structures. It was puzzling. I spent 3.5 years trying to evaluate different options how it can happen. 3 students decided that they're not working on that project anymore. One postdoc escaped from me from United States to Canada. It's close by. Eventually, I think we nailed it down. So the nice thing about it that we indeed can now connect very well the microscopy results and the optical results. And for instance, we can definitely evaluate in large numbers and with great accuracy of shape by using that mammography, and that was done by Zhang, the pitch of this twisted nanowires. I'd like to point out here that the pitch here is in the range of several hundreds of nanometers. Just keep it in mind. In fact, what people who are interested in gold might be interested in, that the same process would be valid for gold. So we illuminated the dispersion of gold nanoparticles with left and right circularly polarized light. And after that, we saw the formation of these kind of sculptures. And these are from gold. And the scale is about, the scale of this arm is about 20 nanometers. It would be interesting to evaluate here the HCM, and I bet it will be greater than for a more spherical structures. But it's hard. We need to evaluate a lot of the images like this. And so we decided to stick with the twisted ribbons that you saw before and evaluate it if we do have the preference of left twist in case of the right twist, and we do. So in fact, the preference here is about 30 to 40% if we use the polarization of specific type. And if we don't, it will be straight wires. This point will be essential a little bit later. So one thing that I like to point out is the existence of this band in circular dichroism and the other band in circular dichroism. That band can be definitely associated with the excitonic transition. So the semiconductors have band gap, and that band gap becomes chiral. The other band is quite interesting. We thought that it actually could be associated with the twist. And later you will see some additional results on that. But now let's look at the mechanism, how light can template the twist in the solid structure. We illuminated the nanoparticles, which are this truncated tetrahedron, at this wavelength. That means that left particles are excited more or preferentially than the right particles. And so, due to the fact that there is some chemical transformation associated with the excited particles, they basically shed off this the layer of stabilizer around them and becoming more active or more active in assembly, they assemble preferentially to the other particles. And so that can be described by this cartoon, and eventually we described it in an atomic scale with precision, which includes water outside and the ionic interactions inside of the assembly of this tetrahedra. And indeed, the twist here, which we obtain in molecular dynamics simulations, and they had been done by Peter Chiral, accurately describe the geometry of the structures. And these simulations are not easy. How do we change from here to something which might be more representative of snails or some other natural things? How do we connect this to something which we can observe around in life? Can we produce these structures which are sometimes we observe around? This is actually my plate in Italy, in Il Ciocco, if somebody have been there. So the pitch here is much shorter. And can we actually control this? Yes, we can reduce the structures. We can control the pitch. And now it is at 50 nanometers. The trick here, or not the trick, but the knowledge here is that we have to change how strongly the rotator interactions at the interfaces of the particles affect the assembly. So it all comes down to the ionic interactions and the length, and how much the contribution of the chiral interactions makes into the assembly of the particles. And eventually, these structures are formed because it's actually a collective effect of all these chiral ligands at the interface. Tell you even more that we have recently obtained the structures with even smaller pitch. And we'd like to control the pitch because we actually would like to understand how the geometry here affects the exotonic transitions, and also it relates to the complexity of the systems. And here are the similar particles which are assembled in the helices, which are actually quite reminiscent of many biological things. One of the interesting things here is the pitch is 10, let's say, is 10 nanometers, one order of magnitude smaller than a twisted nanowires than before, and we still observe that peak at 500 to 700 nanometers. It's unlikely that that peak is associated with actual helicity. It's more likely to be associated with some distortions with the exotonic state. All right, so the other part is I would like to offer you is, you remember this ball, gold ball, which combined the cadmium-Te particles and cytochrome C? If we utilize the anisotropy of the interactions, if we utilize the chirality, we can transition to the structures which you can see here that are the terminal supraparticle structures, which have a crystalline rod inside and a shell of cadmium-Te nanoparticles outside, which are helically wound up. To somebody who is interested in biology, you might be tempted to say that it's actually not. It's representative of the structure of tobacco mosaic virus. So anisotropy and chirality can indeed introduce quite a lot of complexity in the structures. And for the people who are interested in liquid crystals, they also can form extended liquid crystalline structures. And to be quite honest, I would like to call Andy and ask, do we see cusp here?
You think you see cusp?
I love people who answer a question with a question. Yeah. My dad used to do that. All right. So, what are the interesting things that we can work on, and what are the future venues? Light and chirality. I looked at the literature on the origin of homochirality, and a lot of it is associated with the primordial, or actually early universe, emission from galaxies, from new stars, which turned out to be circularly polarized. So it's typically associated with organic transitions, so left is more than right. But I also think that it wouldn't be a bad idea to look at it from an organic standpoint. The nanoparticles are abundant around us, abundant in the universe too. So can it be that this light actually acted not on early organic structures, but rather on very abundant inorganic structures, semiconductors, for instance, carbon structures, Si. A lot of them are catalytic. The other interesting question is indeed the excitants. There is a lot of need to have the chiral excitants, or let's say, or excitons. Unfortunately, and I hope Sasha will work on it more in the future, that we can really understand how the scale of shape and chirality of semiconductor piece can change the optical properties of the excitants inside. The other I mean, the other venues are, of course, chiral catalysis and biological effects. What I also would like to draw your attention that there are a lot of practicality in chiral nanoscale materials. And this is the last part which I'd like to address. The metamaterials, and Thomas had already mentioned that, and other folks too, and the biosensing. In case of metamaterials, the only problem there is the intensity or the power of the rotation. And if we can create a nanomaterial which have the high rotatory power, it will be quite easy to translate, and Peter and I had worked on it in the past, into other devices. And so we decided to form a different type of nanomaterials which would be flat and which would have axes of the rotation or anisotropy aligned with the propagation of the light. So for that we used zinc oxide and deposited gold from one side and from the other side. And in this way, you can make left and right very controllably in nanometer scale. You can see here the SEM results. And Sasha had actually calculated the plasmonic spectrum of the dispersed particles. And again, it would be quite interesting to translate a measure of chirality, some measure of chirality, to here. What I do know that the optical or chiroptical properties of these caps of these gold structures are quite high, and G factor of -0.03 to the best of my knowledge is the highest now obtained. And that enables quite a lot of metamaterials in reflection as well as in transmission. The biosensing story comes back to PCR. It's an efficient technique, and these structures have very strong polarization rotation, in particularly because the helicity is actually accumulates. And indeed, we were able to obtain here attomolar resolution of long DNA strands. And I stress that they're long. They're not short, which would be sufficient for the Raman scattering and the red and blue. Chad Merkin had done a lot of this work, and other people. We also tried to do it with a cancer marker, in particularly with a combination of gold and silver particles. And silver here is added because it has very strong plasmonic effect. And you can see that the plasmonic band associated with the silver is comparable now to the plasmonic band of gold, although it is at the shorter wavelength. You can still see the pairs here. And indeed, the limit of detection here is much better than the close, let's say, it's better, just a little bit, but still better than the close competitor, which is based on the blue red, and it's actually associated with very fundamental optical difference between the optical changes in absorption and optical changes in the polarization rotation. So if we look at, say, intensity of the hotspots, which are essential for Raman scattering as well as for coupling of the particles together and collective plasmons, they're rapidly declining, but the polarization rotatory power on the gap, it has a much more extended dependence. That allows us to plug in that gap the protein, which is quite a bit bigger than traditional gaps, and also extend it to long strands of DNA. And long strands of DNA are genes, are specific. With that, all these people had done tremendous work. And Andrei Ogach deserves my great thanks. And it's Young, he's definitely a genius in the lab. And Ming Yang and San Ho and the more recent people, Yung Long, who is now a professor, Ji Han, she had done the templation of the nanowires and continues doing that. In jail, he was working on the assembly in the terminal structures. Thank you all. Thanks, these folks. This work had started under auspices of Peter quite some time ago. Thank you, Peter. All right, I'll be happy to answer any questions. Oleg.
So you mentioned that as the function of ionic content, you can change the angle between two nanorods. So do you have kind of a plot, a dependency, how the angle, and does it correspond to the basic ideas about, electric double layers? And
Great that you ask. We don't have right now that plot, but this is something that is indeed very it bugs me. The really significant point about the correlation between the double electrical layer and the translation of repulsive interactions of gold rods from each other needs to be made. What we're also learning from other parts of the work, from other parts of the lab, that actually the interactions between nanoparticles at nanometer scale with the gaps of couple of nanometers as here are not actually subject to DLVO. This is the traditional technique. So we cannot really apply it. Therefore, we have to design and devise another method to account for repulsive and attractive interactions, which hasn't been done yet. There are some force fields which are useful, but the correlation and the connection between the ionic strength cannot be done that easily. It has to incorporate a singularity of ionic penetration inside this gap. A single ion can change it dramatically. And that I see one of the fundamental problems that we need to address. Or some other people need to address. Hey, Sasha.
How intensive is light when you do chiral templating? It is
strong.
Weak light. Do you create heating, boiling?
No.
No. It is weak light, right?
It's about, I would say, 4 times stronger than this. It's the laser which are this big.
So you need 10 hours.
Or sometimes longer, yes. So it is a slow process, yes. In fact, illumination occurs over the period of 72 hours to obtain these twisted long structures. Yeah. Heating was a part of our consideration. It doesn't evaporate, it doesn't change with heat, so it doesn't seem like it's a factor.
Continuation of probably Oleg's question. Can you explain the qualitative mechanism, how the sign of the angle actually can change? Because I can imagine that amplitude can change, but if you go from left to right, what's the qualitative?
Yes, that's indeed a really significant point. So here, in between these two rods, there are multiple forces. One of them is the mechanics of DNA, electrostatic repulsion, van der Waals attraction, and steric interactions as well. Yeah. So when we change the ionic strength, we change all of them. And one part of it, which should definitely change, or most likely change, is actually electrostatic polarity of the rods, which eventually leads to a symmetry of the polarization.
Flip the rod in terms of dipole moment, maybe something like that.
That's something I'm thinking about. Yeah, we need to carry out a pretty detailed molecular dynamics simulation on that, and we're en route on that. And Peter Chiral is working on it right now.
Okay, it's a very stimulating part. I really enjoy. Okay, very, very solid result. Okay, you use the circular polarized light. Okay, it radiates. You've got like whatever right hand or left hand twist. Good. Also, you shoot like a right hand of left hand distribution, right? Yeah, you say maybe some is 40%, something like this. Okay. Also, you shoot like CD, but the CD you got spectrum is a symmetry. You shoot like some like spectrum is left hand. This should be the mixture. Just the left hand access is right, or you just
let me
selected all the left hand put together solution. Check the CD.
I think you mean the spectrum here. Is that right?
Yeah, yeah. Because this you like distribution is based on the left hand and the right hand. Okay, but I assume you got the mixture. Some is the left hand,
yes.
Some is the right hand, but it's just the some is the access, right? So you use the CD, you just use the right hand, circular polarized, got the mixture, check CD. Then other mixtures is right?
Not quite. So what happens in this spectrum is it is the spectrum obtained from the dispersion, which had been illuminated for 72 hours.
Okay.
And the initial dispersion was cadmium-T particles, which are stabilized by thioglycolic acid. Thioglycolic acid is not chiral.
Okay.
So the chirality comes either from organization of the ligands on the surface, or from truncation, or both.
Okay.
So what's happening here is that we illuminate initially with one polarization.
Just got only one left hand or the one right hand, or just a mixture together?
We did the mixture too,
Okay.
and then we don't see a CD spectrum.
Okay.
It was at best some kind of very weakened odd shape. But when we do use either right or left helicity of photons, we do see in the end the distinct polarizations of the spectrum that you see here, and their mirror image in respect to each other.
Also, what's about like size distribution? Size distribution, because you only shoot some one image.
Yes.
In a large area, maybe. You know.
Yes.
Yeah. Okay.
Yeah. This is size,
Okay.
not size distribution.
Okay.
We didn't do the length. Yeah. The width of the twisted ribbons has a very narrow size distribution, because in that dimension the width is terminal. So it is restricted by electrostatic repulsion. What's happening here that when the particles come together, they prefer to attach in length because in the side, the same charge of the ribbon and same charge of the particles, they have strong repulsion.
Okay, thank you.
Yeah, so in that dimension, it's actually quite narrow. I don't have the actual data, or I don't remember them.
Okay, thank you.
So if there's no questions, maybe we should move to the coffee break and we can ask Professor Kotov. So please join me to thank Professor Kotov.
Thank you all.